So this is part 2 of solving quadratic equations, and we're going to learn how to solve quadratic equations by a new method, which is called taking roots. In the previous video, we learned to solve quadratic equations by factoring. And since this is a difference of squares, it will factor to a product of conjugates. And once we have factored it, we can use the zero product property to solve the remaining equation. And the zero product property says that if I have the product of any two things, then one of those two factors must be zero. So once we've factored a quadratic equation, we've turned it into a product of two linear equations, so that one of those two factors must be zero. So either x plus 3 equals 0, which occurs when x is negative 3, or x minus 3 equals 0, which occurs when x is equal to 3, making my solution set negative 3 and 3. So in this video, we're going to cover an alternative method, which is solving by taking square roots. So recall that when we solve linear equations, we solve them by isolating the value x. So solving by taking roots kind of starts off in a very similar way. I'm going to isolate my variable, which is the x squared, and I do that by adding 9 to both sides. I'll end up with x squared is equal to 9. Well, now if we think about this reasonably, I know that the square root of 9 is 3, so it would be true that 3 squared would equal 9. However, it's also true that negative 3 squared is equal to 9. And it's because the process of squaring something loses information about the sign of the number. So whether I square a positive number or a negative number, my result will always be positive. That's important because the second step in this process is undoing what this square does by applying the square root. But when I apply the square root, because I'm undoing what the square did, I have to go back to the fact that when I square values, I lose the sign, so that I could have either had a positive or a negative value. So whenever I myself introduce a square root, I need to account for the fact that it could be positive or negative. The result, when I solve this, is a value of x, which ends up being positive or negative, the square root of 9. And since the square root of 9 is just 3, my final answer is plus or minus 3. Now this is an equivalent way of representing the answer as the set notation, negative 3, 3, and you could represent your final answer in either way. So the taking square roots method involves a two-step process. First, you need to isolate your quadratic term. So you need to isolate the quadratic. Second, after we had isolated our quadratic term, we applied square roots. So we're going to apply the inverse operation of squaring, which is the root. And one note, whenever you apply square roots, that you'll have to keep track of is the fact that your solution could be positive or negative. So don't forget when you apply a root to account for the fact that your solution could be positive or negative. When I applied my root, I got plus or minus 3. Let's look at a couple of other examples. Here, my quadratic term is already isolated, so I can go ahead and immediately apply roots in the very first step. And again, as a reminder, you need to account for the fact that your solution could have a positive value or a negative value. So I end up with x is either positive or negative 8, and that is a valid form for my solution. In my second term, you may feel inclined to divide both sides by 9, which is 100% valid. In fact, if we go ahead and do that, if I divide the entire equation by 9, I'll end up with y squared is equal to 25 ninths, so that when I then apply square roots, I'll end up with y is equal to plus or minus the square root of 25/9. Now, just as a reminder that you can break up radicals across division and multiplication. So this is really the square root of 25 over the square root of 9, which reduces to 5/3. There's a second way to solve this. In fact, if you notice that the left-hand side is a perfect square in the very first step, rather than dividing by 9 and taking the square root of the fraction, an alternative way for solving this equation would be to go ahead and apply roots at the very beginning, again remembering to account for the fact that it could be positive or negative. I'll end up with 3y equals positive or negative 5, and then I go ahead and divide both sides by 3, and I'll get the same solution, plus or minus 5/3. So again, two different methods, both 100% valid. Which one you choose is really up to you, whether you like to isolate the variable and then take your roots. I myself like to avoid fractions as long as possible and would go with the second way. In question number 3, it's a little bit more involved because we need to isolate our square. Now, you may look at it and say, hey, I don't have a variable squared. Well, in this case, number 3, the quadratic term is actually the binomial. It's this entire value, w plus 11 squared. So this is the quadratic term I'm going to need to isolate. And I'll do that by adding 800 to both sides so that I am left with 9 times w plus 11 squared is equal to 900. Now in this case, this is a perfect square, so I could go ahead and use the second method, but I make the observation that 9 and 900 actually have a common factor of 9, so that if I were to divide both sides by 9, it would actually make my entire equation much simpler, leaving me with simply w plus 11 squared on this side and 100 on this side. So that when I go to introduce my roots, I'll get the square root of the left, the square root of the right, and it could be a positive or a negative solution. When I take the square root of a square, they're inverse operations, so they are undone. I'm left with w plus 11. And on this side, I'll get plus or minus the square root of 100, which reduces to 10. Now I'm going to subtract. Now I want to come back to what this plus or minus actually means. It's saying you have two equations. So what it actually means is that I have one equation, which is w plus 11 is equal to positive 10. And I have a second equation, which is w plus 11 is equal to negative 10, because it's plus or minus. So I have this equation and this equation, which will give me two answers. When I subtract 11 from both sides of this, I end up with w equals negative 1. And when I subtract 11 from both sides of this, I will end up with w is equal to negative 21. So I should end up with a solution set of negative 1 and negative 21. It is actually possible to solve this simultaneously, meaning both of these equations at the same time, rather than splitting them up into two equations and solving twice. What you could have done is simply subtracted the 11 from both sides, which would give you w equals negative 11 plus or minus 10, and then done that arithmetic in your head. Negative 11 minus 10 would give me negative 21, and negative 11 plus 10 would give me the negative 1, and I end up with the same two numbers I did the other way. Okay, so in question 4, I have x squared minus 27 equals 0. This question is actually unfactorable. So currently, the only method we have for solving it is by taking square roots. So I'll isolate my quadratic term to get x squared is equal to 27. Then I'll apply roots to both sides. Remembering to account for the plus or minus. And what I'll be left with after I've done that is x is equal to plus or minus the square root of 27. But the square root of 27 actually contains a perfect square factor. This is 9 times 3, which makes the square root of 27 equal to the square root of 9 times 3. And as we mentioned in a previous example, radicals can be broken up across multiplication and division, meaning this is the square root of 9 times the square root of 3, which is just 3 times the square root of 3. So this entire equation actually reduces to 3 times the square root of 3. So not only is solving by taking square roots a shortcut in some cases, it also gives us a way for solving questions which were previously unsolvable. Okay, we have one more question, which is a word problem. If 5 is subtracted from twice the square of a negative number, then the difference is 27. What is the number? So recall that when I have a word problem, I should begin by establishing a variable. So I'm going to let x equal the negative number that I'm looking for. And the relationship which is described here is that 5 is subtracted from twice the square of that number, which we've called x. So I'm going to square x, and 5 is subtracted from twice that square. So I'm going to subtract 5 from 2 times the square of that number, and that is 27. That's what's described in this word problem. So now I'm going to go ahead and solve this by applying roots. So I'll get 2x squared, add 5 to both sides, is equal to 32. I'll then go ahead and divide both sides by 2, which will give me 16. And then apply my roots. So I'll take the square root of the left, which will equal the square root of the right, and I have to account for the fact that it could be a positive or a negative solution, which makes x equal to positive or negative square root of 16, which is just 4, representing again the numbers negative 4 and 4. Now, because in this word problem, it started off by saying x is a negative number, I would reject the positive value as it does not satisfy the necessary condition of it being a negative number. Therefore, my final answer is x is equal to negative 4.
Surely you can't be serious.
I am serious. And don't call me Shirley.